Hello guys, welcome back to another video of me showing how cooked I am in A-levels. So yeah, I managed to find this room. I'm at the University of Nottingham right now. I didn't book this room because I'm not a university student. So yeah, someone came here and was like, "Did you book the room? Because we're gonna use it in like an hour." So to summarize, I have exactly half an hour, 29 minutes from now to do all my revision and finish this video. And dude, today was absolutely insane. I cycled like more than 20 kilometers. I'm probably going to cycle 30 to 40 kilometers today. I've been going up and down on my bike, but as someone commented on my YouTube, say Alhamdulillah, you get to do these things. So yeah, we're going to get straight into it. I'm going to go through every lesson of the day in chronological order and go through all the topics and information that I learned throughout the day. First of all, my first lesson, also, I don't have a whiteboard, that's not touchscreen. So inshallah, next video, I'm going to go to a different building or different room, find a whiteboard, then I can actually show you guys what I'm doing. Also, I forgot to invest this video, so it doesn't matter. You don't need to see my working out, this was for myself, and you can just see me struggling. Okay. First lesson of the day was further maths was Mr. Williams. Yeah, I didn't bring a tripod either because I don't want to set that on. Okay, further maths. Further maths with Mr. Williams. Okay, so this was a funny story. For my first period, I had a free period and I was doing US applications, right? Because the deadline is literally in like 11 or 10 days. So after half of that free period had gone, I went to my friends. I was like, "Oh, what are you guys doing?" That's after I forgot my bike light at the university, so I cycled there and went back. Anyways, yeah, I went over to my friends, asked them, "What are you guys doing?" And they said they were doing homework. And I was like, "When? For when? When's the test?" It was next lesson in 30 minutes, okay? So, oh my, it was 60 marks worth of work. And I did not revise for De Marvelous. I did all the exercises, but like, I didn't revise for it. So, yeah. The homework was pretty difficult, okay? But alhamdulillah, the test was the stuff that I had already done before, so it wasn't too bad. And De Marvelous is literally just used for complex numbers. Yeah, it's a theorem for that. I'm gonna explain that for you now. Okay, let's go. Gonna get my maths book. This is for maths, alright. Okay. A pen. Okay. What is a complex number? A complex number is just a different type of number where you have a real part and an imaginary part. So for example, 3 plus 5i is a complex number. And we use Argand diagrams, which is like the equivalent of a Cartesian plane, XY plane, to represent these Argand diagrams. Dude, I sound so smart, but I actually don't know what I'm saying. Anyways, so, for example, this, oh, I can't see anything. But this would be, like, if that was a 3 and that was a 5, that would be on the x-axis 3 and on the y-axis 5. But instead, we call that 3 plus 5i, where this axis is the real axis and that's the imaginary axis, and that's 3 plus 5i. And yes, I know everything is inverted, but deal with it. Okay, so that's a complex number and you can represent them on Argand diagrams. But there's also multiple ways of representing complex numbers. So there's the x plus iy form, which is just like Cartesian coordinates. So let's use 2 plus 2i. X plus iy form of 2 plus 2i is just 2 plus 2i. And then there's also modulus argument form, which is in the form r, where r is a modulus, cos theta plus I sine theta. And theta is the argument. So what is the argument? It's not something where you have a back and forth with someone. An argument in terms of complex numbers is the angle that it makes with the real axis. So for example, this 3 plus 5i, it would make this angle. And by the way, we go anti-clockwise with Argand diagrams, complex numbers. Don't tell me why. Don't ask me why. So there's that, r cos theta plus I sine theta, and then there's e to the I theta form. So e to the I theta. So to actually convert between these two forms, you need to work out the modulus and argument. So we have 2 plus 2i, that's the complex number that we're working with. The modulus of 2 plus 2i is just the square root of 2 squared plus 2 squared. So where did those numbers come from? If we draw another Argand diagram, if we pretend that's an Argand diagram, and that's the origin, that's 2 plus 2i, right? Well, this is 2, the bottom is 2, and on the imaginary axis, that is also 2. The modulus just finds the absolute distance, so the Euclidean distance is the proper way of saying it. But it's also just like the displacement from the origin to the actual point on the Argand diagram. So it's just Pythagoras, basically. So root of 4 plus 4 is 2 root 2. So the modulus is 2 root 2. And the argument is the angle. So you guys know how triangles work. That's a right angle, that's 2, that's 2. It's just tan opposite over adjacent, which is tan 2 over 2. Or tan, inverse tan 2 over 2, which is inverse tan of 1, which is 45 degrees, or what's 45? Pi over 4. So you could represent it in the r cos theta plus I sin theta form as 2 root 2 cos pi over 4 plus I sin pi over 4. And then e to the I theta form would be, oh yeah, there's r e to the I theta, because you have to put the modulus in front of the e. R 2 root 2 e to the I pi over 4. So re to the I theta would be 2 root 2 e to the I pi over 4. And then modulus argument form would be like that. Okay. So that's just an introduction to complex numbers, but that's not even De Morvis theorem. So De Morvis theorem is when you have a complex number. Let's say the complex number is e to the I. No, let's put it in modulus argument form. Let's make it general. So r cos theta plus I sin theta. If we wanted to do z to the power of n, it would be r to the n cos n theta plus I sin n theta. So what De Morvis theorem actually tells us, instead of, using like normal expansion to multiply out these complex numbers, you can, if you're doing the complex number to the power of something, you can actually do the modulus to the power of that, and then the argument multiplied by that number. So you're adding the argument n number of times, and you're multiplying the modulus by itself n number of times. And we're using that to show different things. So, for example, in the homework, you have to show, for example, that cos 5 theta equals all of that. And we can use De Morvis theorem to expand that. So that would be cos 5 theta plus I sin theta. And you can see the modulus is 1. So 1 to the power of 5 is just 1. That's why only the argument is being changed here. So you would have cos 5 theta plus I sin theta equals, and then you actually expand it using binomial theorem. Binomial formula. Okay, anyways, you do that, and if there was, and then you just take the real parts, because cos is just a real part. So let's do, we really don't have time. Oh my days. Okay, I can't go through those with you. But for example, if we had instead of cos 5 theta, so instead of the argument being 5 times bigger, how about if we had cos theta all to the power of 5? Then you would use z plus 1 over z to the power of 5. Because z over 1 over z to the n, where you let z equal e to the I theta, would just equal, so z plus 1 over z n is just the same as, by the way, we need to show what z plus 1 over z would equal. Cos theta plus I sine theta. 1 over z is the same as z to the minus 1. And z is the same as e to the I theta. So 1 over z would be e to the minus I theta, which means you would have plus cos theta, because cos is symmetrical about the y-axis, but you would have minus I sine theta, because sine, if you have a minus argument inside, it's the same. Sine minus theta is the same as minus sine theta. That's essentially it. While cos minus theta is the same as cos theta. Okay, minus I sine theta. So the sine thetas would cancel out, and you'd get left with 2 cos theta. And this is the same with z minus 1 over z. Instead of cancelling out the sines, you would cancel out the causes, and instead you'll be left with 2I sine theta. So you can use that z plus 1 over z equals 2 cos theta, and z minus 1 over z equals 2 sine theta. 2I sine theta, sorry. You can use that to I'm trying to find, yeah, okay, I found the question. For example, here, z minus 1 over z is the same as 2I sine theta, and you can use that to turn it into an equation like this, using trig identities, which is very cool, isn't it? And then roots of unity, for example, you can have z to the power 4 equals 1, for example. So if we draw 1 on an Argand diagram, 1 on an Argand diagram is just over here. So if z to the power 4 equals 1, what does that actually mean? What does that actually mean? I have no idea. It means the modulus is 1 and the argument is 0. So if you add 2 pi to the argument, guess what? You just go back to the same place. But that's the thing. We're not finding z to the 4, we're finding z. So we have z to the 4 equals equals e to the I theta, where theta equals 0 plus 2 pi k. 2 pi k because 2 pi will just like do one whole phase, and k because we can keep going up in integer values. So if we actually wanted z, so z to the power 4 is I to the I theta, which means z is the modulus rooted by 4, which is just 1. So e to the I, and then 2 pi over 4k, which is pi over 2k. It's a bit complicated to explain. Well, it's not, I'm just doing a bad job explaining. So z to the power 4 equals I to the I theta, z equals e to the I pi over 2k, which means to find all the roots of unity, and all the roots of unity are all the possible solutions to the equation. And roots of unity just means when it's equal to 1. You would go through the different values of k. And in this case, because we want 4 solutions, z to the power 4, we can have a k value of 0, 1, 2, and 3. Why don't we use 4? Because if we use 4, we'll get a repeated solution of 0. So our values of z would be e to the, when k is 0, it will be e to the 0, which is just 1, which is our initial solution. We would have e to the theta over 2i, e to the pi over 2i, and then e to the 3 over 2 pi I. And these would be all of our solutions. Okay, that's the end of De Moivre's. Oh my days, I have four more lessons to go through. That's insane. Sorry, that's, oh my lord. Subhanallah. Okay. How am I going to... Oh, someone just went at the door. I think they want to enter the classroom. Dude, I have more work to do. We started a new thing called differences. Let's go through a question real quick. Dude, this video is going to be like an hour long, you know? It's absolutely insane. So yeah, I still haven't handed this homework in, because I did it after the test. I'm gonna get the differences work. I'll be back real quick. Okay. Oh my days. I am so behind on work, by the way. And I'm working literally like 24/7. It's absolutely mental. I don't understand how other people do it. This is so fun though. I can't lie, this is so fun. Okay. I need to get the further maths, I think. Core Pure Year 2 textbook. Solutions. Nice. Okay. As you can see, I have my laptop here. I'm opening the textbook right next to me. And what? Oh, we're on series now. We're on a different chapter. Very fun. Okay. Oh, that looks complicated. No, that looks complicated. Okay. Okay. I've got it, I think. Okay, let's do one of these questions. Alright, cool. So, we're gonna start. No! We're gonna start. Bro, chill. I can't see what you're seeing, by the way. So we're gonna start with this question. Dude. Oh my days. Anyways. Please, I don't want to do this. Dude, just please. My phone is like very slippery. It was okay. I'm gonna use my pencil case because my pencil case is heavier to support my phone. Anyways, so we have to show that this is a easy exercise at the moment, by the way, especially compared to complex numbers, which my further maths teacher said was the most difficult topic in the entire textbook for year 2 further maths. Anyways, 1a, show that r is identical to 1 over 2 r plus 1 minus r minus 1. So with this question, you just have to expand the right hand side and make it equal to the left hand side. So that's what I'm going to do. Right hand side equals 1 over 2 r squared plus r minus r squared plus r, which is 1 over 2 2r, which just gives r. Okay, so that's step 1 done. Hence show that. And then here you need to substitute different values of r. That made me sound so weird. Okay. Bismillahir Rahmanir Rahim. Okay, anyway, sorry. When r equals 1, you know, it would be so much easier to have a whiteboard because now you can't see anything I'm doing. 1 over 2, when r equals 2, 2 over 2, 3, when r equals 3, 3 over 2, 4. How much time do I have? 10 minutes. Equals 1, equals 3, equals, and I'm not sure if I'm doing this correctly, equals 6. Dude, I'm not doing this correctly. What? Oh, I wasn't using the formula. guys. Okay, I was substituting into the wrong thing. Equals a half, and then 1, 2 minus 1, 0 equals 2 half. 2. Alright, cool. They cancel out. Okay. So, as you can see, I just plugged in values of r equals 1, r equals 2, and you can see that this term is the same as this term here, which means you can cancel them out because you're adding one and then you're taking away the other one. So in reality, you're left with n minus n, okay, a half of everything, and n plus 1 minus n minus 1. You know, I haven't done a single question on this topic, so I have no idea if I'm doing it right. I need to check the mark scheme for this one. 2A series. They cancel out, yeah. So what? Okay. That's weird, man. That's weird. That's weird. That's strange. Oh no. That does not look good. You know, they use r equals n minus 1 instead of the 1, 2, 3, 4 thing. I'm gonna leave that for tomorrow. We need to move on to a different subject. Okay, so that was further maths. After further maths, I had computer science. Okay, computer science, I'm gonna get that out. Oh, very nice, very nice. As you can see, this is why I'm absolutely stressed. So with computer science, we were doing theory of computation, regular expressions. So in our last lesson, we did finite state machines. Finite state machines are a conceptual model, I think, for me. Finite state machine meaning. It's an abstract model that's used to validate a set of inputs, because it can only exist in one of many states at the same time, and a finite state machine can also be called it can also be called a state transition diagram, which is very strange. Okay, that is so cool, man. So finite state machines, as you can see, you can have circles with 2 borders on them and circles with 1 border on them. So what's the difference? Well, the circles with 2 borders on them, those are called the finite state, and it's the final state that you want to get to validate a set of inputs. If you go through a set of inputs and it doesn't end on that circle with 2 borders on it, then that means it's not a valid set of inputs. So you can use this to represent different things. For example, a password validator, an email address validator, or postcode validator. And what we learned in today's lesson was how to convert these finite state diagrams into regular expressions. So I want to go through the different operators in regular expressions. So we firstly have the asterisks. Asterisk means you can have 0 or more of the value that's preceding it. Regular expressions is a prefix, so you have the value and then the operator. And then there's in order and postfix, which are different things. And reverse Polish notation is when it's prefix notation, right? Reverse Polish notation. It's postfix. Wait, what? Wait. Oh, okay, so regex is not prefix, it's postfix, because the operator is after the value, which is the same as reverse Polish notation. Anyways, if you have a plus, that is 1 or more occurrences of the value preceding it. If you have a question mark, that's 0 or 1 occurrence of the value preceding it. If you have a pipe symbol, which is just a horizontal line, then that's an OR symbol, so either the value on the left or the value on the right, and then brackets is a capture group. So if you want to repeat the values A, B a certain number of times, you put them in a capture group, and then you can use an operator after it. Oh my days. Okay, no, I'm looking at the time that I have. The symbol here, not sure if you can see, means an empty set. Regular expressions can work with text patterns because they match patterns in text files. Any language which is a finite state machine will also be known as a regular language. Interesting. So, regular expressions are used to specify a set of strings that satisfy given conditions. So, for example, we went through this finite state machine, and the reason it starts with AA is because if you want to get to this final output, you can only do A and A. If you do A and B and whatever set of values, you'll be stuck in this loop. But the only way to get here would be to do 2 A's, and then you can do the rest with... Also, we didn't figure out the answer because it was so complicated. But yeah, that was that lesson, regular expressions. Let me just check that it is called a finite state. I'm going to check the previous regular expressions lesson. Oh, a Mealy machine is a finite state machine that returns an output. Very cool. Cardinality is how many elements are in a set. Cardinality, dude, the number of elements in a finite set. And an infinite set is a set whose... What? This is all wrong. Dude. Oh my. Okay. And a set is countable if it can be counted off against a subset of the natural numbers. Infinite set is one which has no end value. A finite set is a set whose elements can be counted off by natural numbers up to a particular number. Okay, anyways, that's computer science. I had maths, computer science, and then maths again. And then we did differential equations, which I have no idea about. And then physics. Dude, I don't have enough time. I'm going to have to carry this on somewhere else. That's so sad. That's really so sad. But physics we did. So I'm not gonna bother with finishing off this lesson because that means I'm gonna have to find another room and then finish it off there. So I'm just gonna explain it to you like now. So we did differential equations. I don't really know what else to explain because I was doing Demarva's further maths homework in that lesson. And then in physics we have a radioactivity test on Wednesday and I haven't started revising for it. What were we doing in physics? We were doing more stuff on radioactivity, but we were doing, what's it called? Fusion and fission, but what was the energy called? Bonding energy. No, it wasn't. Sorry about that, I just saw. Okay, here. Binding energy, alright. So, we were doing binding energy in physics, where we have... Binding energy is the work done to split a nucleus into its nucleons. And fusion is more effective than fission because there's a greater difference between the binding energy between the lighter nuclei and the stable nuclei, whereas with the heavy nuclei there's a very low difference in binding energy, as you can see here with this binding energy per nucleon curve. And then we can use the mass deficit, I think. Mass defect to work out the binding energy of the of the element. So you calculate, you add the total mass of the protons, total mass of the nucleons, take away the total mass of the actual element, or the atom, sorry, the nucleus, and then you multiply that by, or you convert that mass into energy, into electron volts, and then divide that by the number of nucleons, and then you get the binding energy per nucleon. Yeah. So the stable ones are the ones at the top of the binding energy per nucleon curve, because why are they the most stable? I'm not sure. As the highest binding energy, they're the most stable because they have the most binding energy. Because they need the most energy to break them apart, so obviously they're going to be the most stable, because they do not break apart easily. Anyways, that's the end of our lesson. I hope you enjoyed. I'm going to get kicked out very, very soon because I'm 1 minute over my stay. Or no, 2 minutes actually. So peace out, and I'll see you in the next video. Assalamu alaikum wa rahmatullahi wa barakatuh.